Introduction to Quantum Information Processing. Welcome to Lecture 16. Last lecture, we saw how to express quantum measurements and quantum channels in terms of Kraus operators. In this lecture, I'm going to show you another form for expressing state transitions called the Stinespring form. The Stinespring form of a measurement is the following. Imagine that the input state is a d-dimensional system. First, we add an m-dimensional ancilla in some computational basis state to our system. Say the state ket 0. The combined system is md-dimensional. Next, we apply some md by md unitary operation u to the combined system. Then we measure one register in the computational basis, yielding a classical outcome k and a residual quantum state in the other register. The circuit diagram is drawn with two registers going into U, an m-dimensional register and a d-dimensional register. These can also be the registers that come out of U, but we're going to also allow the dimensions of the outgoing registers to be different, as long as the total dimension is the same. So the outgoing registers can have dimensions L and C as long as L times C equals M times D. To get a feeling for this, consider the case where all the dimensions are powers of 2. In that case, we can assume that each register is a bunch of qubits. For example, we equate the case of a 4-dimensional register with computational basis ket 0, 1, 2, and 3 with the case of 2 qubits with computational basis ket 0, 0, 0, 1, 1, 0, and 1, 1. We make no distinction between the two ways of looking at such a register. Then our Stinespring circuit looks like this. In this example, the input state is 5 qubits, whereas the residual outgoing state is 4 qubits. Also, the ancilla is 2 qubits, whereas the number of qubits that are measured is 3. As long as the total number of qubits going into U and coming out of U is preserved, this makes perfect sense. Also, note that some of the dimensions can be 1. A one-dimensional register is essentially the same as no register. The density matrix would be a 1-by-1 matrix with entry 1. If you take a tensor product of this with another matrix, then, well, nothing happens to that other matrix. For example, if m equals 1, then there is no ancilla. In our qubit scenario, this translates into 0 ancilla qubits. Remember those measurements that I called exotic measurements? It should be clear that those measurements are subsumed by these Stinespring measurements. Okay, so I've explained what I mean by a Stinespring measurement. What about channels? As we noted earlier, one way of thinking about a channel is as a measurement where we don't look at the classical part of the outcome. So we could define Stinespring channels that way here. We'll do that, but we'll simplify things by noting that if we're not going to see the classical outcome, then instead of performing the measurement, we can trace out the register like this. Notice the circuit notation that I'm using for tracing out a register. The imagery is supposed to be that we just toss that register away. Stinespring measurements capture all of the simple types of measurement that we've encountered before. For example, a measurement in the computational basis, where we just see the classical outcome, corresponds to the case where there is no ancilla and no residual state, and U is the identity. Measuring with respect to an arbitrary orthonormal basis is a slight extension to this, where U performs the relevant basis change. And measuring one of two registers is also captured. If we have an L-dimensional register and a C-dimensional register, and we wish to measure just the L-dimensional register, then there is no ancilla, and we set the incoming dimension D to L times C. Now, let's look at some basic channels. The unitary channel is easy. No ancilla and no register to trace out. Here's the operation of adding an m-dimensional ancilla to an incoming state of dimension D. There is no register to trace out, and the residual state has dimension md. And here's the partial trace. All these examples so far are kind of trivial examples. Here's a slightly more interesting channel. Remember the qubit decoherence channel, corresponding to the residual state when a qubit is measured in the computational basis, and we don't see the classical part of the outcome? Is there a Stinespring circuit for this? Here's a Stinespring circuit for this. How does it work? Well, consider the case of a pure state with amplitudes alpha 0 and alpha 1. The C0 gate causes the two qubits to become entangled in this manner. Then, when we trace out one of the two registers, the resulting density matrix becomes this, with the off-diagonal entries zeroed out. So, at least we've seen that this works for pure states, and I'll leave it to you to verify that it works for the case of mixed states. Here's a very simple channel that I haven't discussed before that I'll call the reset channel. The input is a qubit, and the output is a qubit in state ket 0, and that's regardless of what state the input qubit is. It maps every qubit to the ket 0 state. Here's a Stinespring circuit for this. The idea is very simple. It's like I have a shelf filled with qubits that are all in state ket 0. Then you give me a qubit, and what I do is I toss that qubit away, and what I give you back is a qubit from my shelf. Here's another way of denoting the same circuit with a box representing the swap gate. Denoting the swap gate this way emphasizes that it's just a particular 4x4 unitary matrix. Okay, this is all pretty simple so far, but here's an interesting exercise. Can you come up with Kraus operators that represent the reset channels? I don't think this is at all obvious from what we've seen so far, but perhaps you can see a clever way of figuring this out. I recommend that you pause now and spend a little bit of time thinking about this. The answer to this will become clear from things that I'll say later on during this lecture. Here's another interesting channel called the depolarizing channel. This channel is somewhat fundamental as a model of noise, and we'll be seeing more of it when we get to the subject of quantum error correcting codes. The channel maps qubits to qubits. The output qubit is a probabilistic mixture of the input state and the highly mixed state whose density matrix is diagonal with entries 1/2 along the diagonal. By the way, that mixed state is called the maximally mixed state. The probabilistic mixture depends on a parameter p between 0 and 1. With probability p, the state is left alone, and with probability 1 minus p, the state is changed to the maximally mixed state. Here's what the effect of the channel looks like on the block sphere. The maximally mixed state is the state at the center of the block sphere. The channel moves states towards the center. In fact, the channel shrinks the entire block sphere by a factor of p towards the center. So that's what the depolarizing channel does. Can we represent this channel in Stinespring form? Here's a Stinespring circuit for this channel. At first glance, this circuit may look complicated, but we can understand it by first looking at the two middle qubits. The Hadamard and C0 gate are manufacturing a Bell state. Note that each qubit of the Bell state is in a maximally mixed state. The rest of the circuit can be viewed as either swapping the input state with the maximally mixed state or leaving it alone. Think of the unitary operation R as setting the control qubit to the controlled swap gate to 1 with probability p. Actually, it's not really doing that. What it's really doing is creating a superposition of ket 0 and ket 1 with amplitude square root of p on ket 0. But the net effect of R in this context is mathematically equivalent to the probabilistic procedure that I described. Notice that the Stinespring form uses 3 ancilla qubits. Is there a Stinespring form that uses fewer ancilla qubits? I'll leave it as an exercise to come up with a Stinespring form for this channel that uses only 2 ancilla qubits. And here's a real challenge question. Is 2 the minimum number of ancilla qubits for the depolarizing channel, or can it be done with only 1 ancilla qubit? Either prove that 2 is the smallest, or show that it can be done with 1. Now, let's recall the Kraus form for measurements and channels that I explained in the previous lecture. A set of matrices are called Kraus operators if they satisfy this equation. Associated with any set of Kraus operators, we have a Kraus measurement, defined this way, and a Kraus channel, defined this way. We're now going to look at 2 theorems. The first theorem is that any transformation in the Kraus form can be simulated in the Stinespring form. The second theorem is that any transformation in the Stinespring form can be simulated in the Kraus form. Let's start with the first theorem about simulating Kraus forms by Stinespring forms. The defining equation of Kraus operators may look a bit mysterious. Here's another way of looking at it. Suppose we have a set of L C by D matrices, and we stack them like this in a block matrix. This block matrix has L times C rows and D columns. What's interesting is that the columns of the block matrix are orthonormal vectors if and only if the set of matrices satisfies the Kraus equation. To see why this is so, consider all the inner products of the columns. If we left multiply the block matrix by its conjugate transpose, then the ijth entry of the product is the inner product of the ith column vector with the jth column vector. If the vectors are orthonormal, then this inner product should be 1 if I equals j, and 0 if I is not equal to j. In other words, the product should be the identity matrix. This product of the block matrices is also equal to the expression of the Kraus form. It follows that we have Kraus operators if and only if the columns of the block matrix are orthonormal. One corollary of this is that D must be less than or equal to LC. Otherwise, the number of orthonormal vectors would have to exceed the dimension of the space in which they exist, which is impossible. So we have L Kraus operators that are C by D matrices, and D is less than or equal to LC. To make the dimensions work out nicely, I'd like to assume that D divides LC. For this to hold, we might have to increase L. It's straightforward to show that this can be done where the new value of L is less than double the original value of L. Since L is the number of Kraus operators, if L is increased, we need to add more Kraus operators. We can set all the new Kraus operators to 0 matrices. Note that the larger set of matrices are still Kraus operators. So we can assume that D divides LC and set M to be LC divided by D. Then we have LC equal to MD. Now, consider the block matrix of Kraus operators again. Its columns are orthonormal. We can extend this set of LC dimensional column vectors to be an orthonormal basis of size LC. If we add these column vectors to the block matrix, we end up with a square matrix that's unitary. Call this matrix U. It's an LC by LC matrix. Now consider this circuit. The input to the circuit is 2 registers, an m-dimensional ancilla and our d-dimensional input state. The circuit applies U to this. What's the output state? Let's calculate the output state. The density matrix of the input state is the m by m block matrix in the middle with rho in the top left corner. We conjugate this by U. The product of the first 2 matrices is as written here. Notice that each Kraus operator is a C by D matrix, so the dimensions match for the blocks. Now we continue evaluating the matrix product and we get this. Note that this output matrix is an L by L matrix consisting of C by C blocks. So we can think of the output state as consisting of an L-dimensional register and a C-dimensional register. Call the state produced so far mu. What happens if we trace out the first register of mu? According to the definition of the partial trace, it's the sum of the D by D blocks along the diagonal, which exactly matches the definition of the Kraus channel that we started with. What happens if we measure the first register of mu? The probability of outcome k is this expression, where the kth projector masks out all the blocks of mu except the kth block. So the trace is consistent with the definition of the outcome probabilities arising in the Kraus measurement. That's how we convert a Kraus form to a Stinespring form. Okay, what about converting in the other direction? Here we have two Stinespring forms, a channel and a measurement. How do we show that these can be expressed in the Kraus form? Would you like to pause now and think about this before I give an explanation? Okay, the conversion to Kraus is fairly simple. It's based on two ideas. The first idea is that for all the operations that occur within these Stinespring circuits, we already know how to express those operations in Kraus form. We have a Kraus form for adding an ancilla. We have a Kraus form for applying a unitary. We have a Kraus form for tracing out a register. We have a Kraus form for measuring a register. So all we need to do is combine these. The second idea is that if we have two Kraus channels, then we can compose them to get a Kraus channel for the combined system. I'll leave it at that. The way I've been describing things so far is as if there's a dichotomy between measurements and channels. You either measure and get a classical outcome and a residual state, or you apply a channel and get just a quantum state as outcome. In fact, there's a general notion that unifies these. Let f be some function from the set of all measurement outcomes to some other set t. Suppose that we apply the Kraus measurement and then we apply f to the classical outcome. So for outcome k, what we see is not k, but f of k. If f is a constant function, then seeing f of k provides us with no information about k. So that corresponds to the case of a channel. The other extreme is where f is a bijection, for which knowing f of k provides full information about k. And there are in-between cases where f is not constant nor a bijection. In those cases, we receive partial information about k. What we see might narrow down the value of k to some subset of all of the possibilities. A final topic concerns POVM measurements. First, a word about terminology. POVM stands for Positive Operator Valued Measure, which is a generalization of the notion of a measure that you may have seen in probability theory or functional analysis. This word measure means something else than our notion of a quantum measurement. So if we're speaking about a measurement, then we really want to say POVM measurement as opposed to just saying POVM. Okay, so what are POVM measurements? They are a simplification of Kraus measurements that works provided that we only care about the classical outcome, where we don't care about the residual quantum state. Recall that for a Kraus measurement, the probability of outcome k is this, and we can cyclically permute the arguments of the trace function to this. For each Kraus operator ak, define ek to be ak star ak. It turns out that all we need to know is this ek to define the outcome probability. With this in mind, we define a set of square matrices E0, E1 up to EL-1 to be POVM elements if they have these properties. They are all positive, meaning that they are Hermitian, and all their eigenvalues are greater than or equal to 0. And they sum to the identity matrix. Then the associated POVM measurement is defined so as to have outcome k with probability the trace of rho ek, where rho is the state being measured. A word of caution. For a POVM measurement, there is no way to define a residual state. This is because we cannot uniquely deduce a set of underlying Kraus operators from a set of POVM elements. We can find an AK such that EK equals AK star AK, but this AK is not unique. And for a different choice of AKs, the residual state would be different. So we need the Kraus operators if we want to be able to talk about the residual state after the measurement. Okay, let's end the lecture now.